Okay, so let's take a look at the do now for today. Today we're talking about volumes of known cross sections, and it's going to be helpful for us before I go into my whole explanation of how you actually make these figures to understand how to make the area of a square or equilateral triangle or isosceles right triangle or semicircle based on just knowing one side length. So just knowing this side length is d, what will be the area of that square? Well, obviously area of a square is length times width, so that comes out to be d squared. Okay, I would say that's a pretty important known cross-section formula because that's going to come up in almost every single situation we're going to work on today. Equilateral triangle. Equilateral triangles are based on doing 60 degrees on each side. If you draw an altitude of this equilateral triangle, it breaks up the base into, instead of just being d, each length would be 1/2 of d. If I use proportions in an equilateral triangle, it turns out that this height comes out to be radical 3 over 2d. Okay, again, this is proportions in equilateral triangles. And so then therefore, if I do my whole area calculation, that's 1/2 the base of my entire triangle, which is d, times my height, which is radical 3 over 2 times d. That's how I end up with radical 3 over 4 d squared. I don't think you're going to see isosceles right triangle pop up all that often, but that one would come out to be 1/4 d squared if you just want to memorize that. Semicircle, I think, is probably going to be the next most common one other than squares. So let's talk about making the area of a semicircle based on knowing its diameter. Okay, so if you think about the fact that diameter is equal to twice the radius, area of a semicircle is normally pi r squared over 2. Well, if I rearrange this diameter formula, instead of being d equals 2r to r equals d divided by 2, I could plug that in here. So I'd have pi over 2 times d over 2 squared. That comes out to be pi over 2 times d squared over 4, or pi over 8d squared. I think out of these formulas, I really think you should make sure you know the square and the semicircle. Okay, so today we're going to talk about making volumes with what we call known cross sections. So the biggest thing that's different with this is that instead of taking a region and revolving it around an axis to create these washers, now you're going to have different types of cross sections, like you can see here on the right hand side, that you're going to still be stacking together, so you're still integrating, but instead of doing pi r squared, because that was for a circle, now it's going to change based on whatever cross section is going to be popping out of the page. So that's the idea. You want to think of, you're looking at this region right here, and you want to imagine that popping out of the page at you at each of these locations as I slide across this region is going to be some sort of a square or a semicircle or an equilateral triangle or something like that. I want to point out before I get started on this is that I have the technology to be able to show you what this looks like, but you're not going to be able to really think of what this looks like when you're doing this calculation. So if you just trust the way that it's actually constructed, integrating a cross section, don't worry about what the figure actually looks like. To give you an example of what this one in particular looks like, let me kind of tilt this around. Okay, so you want to think about, again, I'm adding up squares as I go from left to right, and as I do that, it creates the volume of this solid figure. So let me see if I can rotate this just a little bit, and you can see right here, as I move this square from the beginning of the region to the end of the region, again, kind of like when I was stacking those CDs, now I'm stacking squares. All together, it's going to create the volume of this entire region. Okay, so how do we go back and figure out how we can, come up with the area of each of those individual squares? Okay, so what you want to do is you want to think about, you're going to see this view. You're going to see some sort of shape. You're going to see an upper curve. You're going to see a lower curve. You want to find the distance across that region, and from that one distance, we want to come up with a formula that we can use to create the volume, or to create the area of just that one shape. Okay, so imagine that right down here along the bottom of this square, that's actually the length that you're looking at right here. Let's say that that's the distance across our region. How do we find the area of that square? D squared. Okay, so each of these individual squares, as I add them up from the beginning of the region till the end of the region, is going to be d squared. Integrating from the beginning of the region till the end of the region is going to create the volume of my figure. How does this change if it's semicircles? Okay, so let's take a look. What does it look like if it's different with semicircles? So let me just tilt this a little bit, and you can see, once again, the idea is that you're supposed to be thinking about having semicircles popping out of the page at you. Okay, the back side is going to be flat, the front side is going to be circular, and again, the general idea, even though you're not going to have, it's not going to be easy for you to visualize it, if you can find a way to represent the area of this one semicircle based on this distance across the region, and then add all those semicircles, that's integral, from the beginning of the region to the end, that's going to create the volume of this figure. Okay, so that's where we had come up with that formula of pi over 8 d squared. So if I integrate from the beginning of the region to the end of the region, pi over 8 d squared, that adds all of these semicircles together. You can see that if I switch to something more like an equilateral triangle, which again was radical 3 over 4 d squared, as I integrate from the beginning of the region to the end of the region, I create some three-dimensional figure. So once again, don't get fixated so much on what it looks like, think more about the way it's constructed. Integrate the cross-section formula from the beginning of the region to the end of the region, and the cross-section formula here is always based on d, the distance across your region. Okay, so as I just mentioned, it's going to be difficult for you to visualize what these figures actually look like, but think about the way that they're being constructed. You're just integrating each individual cross-section formula. I do want to point out there's no extra pi's or anything in these like you did with volumes of revolution, unless it calls for it because it's a semicircle or something like that. So similar to what we did with area and volume, I think the first thing you should do is graph your function and draw a sketch of what it looks like on that window. You're going to need its intersections again as the bounds of your region. So if you were to graph this function, you'd end up seeing a parabola and a line that look like they intersect at -1 and 2. Okay, that's what your figure look like. So again, you need your distance across your region. That's what we're going to refer to as d. And what's nice, and how this kind of connects to previous stuff, d is the difference between the upper function and the lower function. Okay, so I think the first thing you should do in these problems is probably label, okay, so like this is my f of x, and this is my g of x. So in this specific problem, you're going to be using the idea that d is equal to the upper function, which is actually the linear one, g of x, minus the parabola, which is f of x. So when I go and I plug those in my calculator, let's say I had plugged in f of x as y1 and g of x as y2, this means in my calculator I'm always going to be putting y2 minus y1 wherever I want that d value to be. Okay, honestly, the hardest part is what you've just done. Figure out what it looks like, figure out what the bounds of the region are going to be, and then on top of that, just memorize what are your cross-section formulas. So let's start with squares. Okay, if I was integrating and putting all these squares together, imagine again, you're adding a square popping out of the page at you as you move from the beginning of the region to the end of the region. It would be an integral from -1 to 2 of just d squared dx. Okay, so now just be careful, because again, if you're typing this in your calculator, you might be typing this in terms of y1 and y2. You'll be typing it as -1 to 2, in parentheses, y2 minus y1 whole quantity squared dx, instead of each one individually squared, because you're dealing with a different cross-section formula. Okay, so that value comes out to be exactly 30.6. Okay, so now as I move on to my other cross sections, again, it should be relatively simple because the whole idea is you're just adding all these cross sections together. You're still on the same exact region, same exact function, same upper, same lower, so the d value doesn't change, the bounds don't change. All that really changes is that extra little constant that went in front of d squared. Remember, for equilateral triangles, it's radical 3 over 4 d squared, or isosceles right triangles, it's 1/4 d squared, or semicircles, which I think is probably more common than the two triangles, pi over 8 d squared. So I'm just going to set up the next couple, and you can go ahead and plug them in your calculator if you'd like to figure them out at that point. So for the second one, again, I'm doing those equilateral triangles, same bounds, still d squared dx, except now you're going to put a radical 3 over 4 in front of that d squared for equilateral triangles. Or if it's isosceles right triangles, it's going to be integral from -1 to 2, still d squared dx, but now it's going to be a 1/4 in the front. And finally, for semicircles, it's going to be integral from -1 to 2, pi over 8 d squared dx. Okay, so the whole idea is that, again, you're adding up each of these cross sections on the interval from 1 to 2, and as you stack them together from left to right, Just like we had stacked our circles together when we were revolving around an axis, you end up creating a volume of a solid figure. I'd like to point out really quickly, the only one that had pi in it was the semicircle formula. None of these other cross-section formulas had pi in them because of the fact that you're not revolving around an axis anymore, you're just strictly adding known cross-sections together. Okay, so let's take a look at the setup for another example. So let's take a look at number 2. It says find the volume of the solid whose base is bounded by a circle, whose center is the origin and radius is 10, with the indicated cross-sections drawn perpendicular to the x-axis. So think about a circle centered at the origin. That would be x squared plus y squared equals 100. If I want to be able to plug this in my calculator as functions, I'll have to solve this to get y by itself. So that would be y squared equals 100 minus x squared. As I take the square root of both sides to get y by itself, remember there's a plus or minus version. Where that comes in handy in these problems is that if you were sketching a circle centered at the origin with a radius of 10, the upper half of the circle is the positive version of that 100 minus x squared, and then the lower half of the circle is the negative version of the 100 minus x squared. So your d value, just give me a second to switch colors, is your upper function minus your lower function. Okay, in this case, your upper function would be the positive 100 minus x squared. Your lower function is the negative square root of 100 minus x squared. Or if you simplify that, that's 2 times 100 minus x squared. Which sort of makes sense because, again, you're doubling the distance it would have taken for you to get from the circle down to the x-axis. So that's your d value. Now you're adding all of these d's together on what region? Okay, so where does this start? Well, think about the fact that your circle has a radius of 10. What point would this be? This would be at negative 10, 0. All the way to the right would be at 10, 0. Well, those are now going to be the bounds of your integral. Again, I'm going to just practice with setting up these integrals. You're welcome to go and plug them in your calculator if you want to see like the full answers. But each one of these is going to be an integral that goes from negative 10 to 10. Okay, each one of these is going to be an integral that has a d squared in it. Okay, all you have to remember is what's the actual constant that goes in front of it, and how do you set up your d and find your bounds. Honestly, again, the setup in the beginning of finding what's the upper minus the lower, what's the bound on the left and the bound on the right, that's the hard part. The rest of it is just memorizing. Well, thankfully for squares, it is just d squared. Okay, so that's number 1. For number 2, equilateral triangles, you just have to remember there's a radical 3 over 4 in the front. For number 3, the isosceles triangles, there's a 1/4 in the front. And finally, the last one, okay, letter D, the semicircles, is pi over 8 d squared dx. If there was one, and I can't really imagine too many that you're going to get like this, but if there was one that said that you had to have cross-sections that are perpendicular to the y-axis, the big thing with that is that you would have to change everything to be in terms of y. So let's take a look at what this looks like. I'm going to actually start by plugging this in my calculator and graphing these as they were already given to me. Y equals x squared, obviously you know is a parabola, and ln of x plus 1. So I have x squared and ln of x plus 1. And what you'll notice is that this is the region that we're talking about. And now we want to have where you have these cross sections that are perpendicular to the y-axis. Okay, so actually let me get rid of those little markings and zoom in for a second. You want to picture that your d value is now going across your region like this. And at each of those locations, a semicircle is popping out of the region at you. So again, you want to now think about the fact that you need everything to be in terms of y. What's the lowest y value that we're at? 0. What's the highest y value that we're at? We'll go in your calculator and find the intersection of these two functions and get the y coordinate of the intersection. You'll see that that's at 0.558. Okay, so when I set up my integral for this problem, everything has to be in terms of y. Integral goes from 0 to 0.558. It's going to be d squared. It's going to be dy, because now you're doing everything in terms of y. Okay, so I still just have to figure out how do I represent what d is in terms of these functions. So keep in mind, we're perpendicular to the y-axis, so everything has to be in terms of y. That actually means I have to change my functions to be in terms of y as well. So if I take y equals x squared, and square root both sides. This gives me x equals the square root of y. If I take y equals the ln of x plus 1, and I raise both sides to be exponents of e and ln will cancel out, so I'll have e to the y equals x plus 1, or x is equal to e to the y minus 1. Okay, so the question is, what's my upper, what's my lower? It's really what's my outer and what's my inner. Okay, so technically the one that's further on the right, which stems from x squared or square root of y, that's technically going to be the quote-unquote upper function in this situation. Minus, then obviously the other one, e to the y minus 1. And again, when you plug this in your calculator, you would have to plug those in as x's. This would definitely be like a setup but do not solve, but just in case you